This is experiment A11, investigation of the characteristics of a refrigeration compressor. After watching this video, you should be able to understand the changes in the mechanical and volumetric efficiencies of a refrigeration compressor operating under different compressor loads and compression pressure ratios. The equipment we are going to use for this experiment is the refrigeration laboratory unit manufactured by PA Hilton Limited. It consists of a twin-cylinder compressor driven by an AC motor, a water-cooled refrigerant condenser, a thermostatically controlled expansion valve, and lastly an evaporator. The unit is also equipped with a dynamometer for measuring the motor power output to the compressor, 2 flow meters for measuring the mass flow rates of the cooling water and refrigerant, 8 temperature sensors for measuring the refrigerant and cooling water temperatures at different locations in the unit, and 2 pressure gauges for measuring the refrigerant pressure at the condenser and the evaporator. A handheld tachometer will be used for measuring the compressor shaft speed. There is a water tap behind the unit for supplying the cooling water to the condenser. Ensure that it is turned on. Adjust the mass flow rate of cooling water through the condenser to about 40 grams per second as shown on the cooling water flow meter on the right hand side. Turn the evaporator heat input control knob fully anti-clockwise. Make sure that the diverter valve is set so that the liquid refrigerant is directed to pass through the liquid to vapor heat exchanger. Switch on the unit and increase the heat load to the evaporator to 200 watts. Heat load is calculated from the product of current and voltage, whose values can be read from the ammeter and the voltmeter. At the same time, adjust the flow rate of the cooling water so that the compressor discharge pressure is maintained at an absolute pressure of approximately 1000 kilonewtons per square meter. This is equivalent to maintaining the compressor gauge pressure at 900 kilonewtons per square meter. Now let the unit run for 5 minutes to achieve steady state operation. After the operation of the unit becomes steady, measure the tension in the spring balance, F in newtons, which gives a reading of the force acting at the arm needed to balance the torque developed. To obtain the reading, loosen the knob and move the upper end of the spring balance until the 2 pointers are level. Note that the scale divisions of the spring balance are 0.25 newtons. Next, measure the rotational speed N of the compressor using the handheld tachometer. Point the tachometer at the light reflector sheet around the axle of the compressor. Press the button labelled Measure and record the value of the rotational speed in revolutions per minute, or RPM. Then measure the mass flow rate of refrigerant, MR, using the refrigerant flow meter on the left hand side. Record the suction pressure P1, which is equal to the evaporator pressure. Record the discharge pressure P2, which is equal to the condenser pressure. Also record the refrigerant temperatures T1 to T6 at different locations in the unit. These correspond to the compressor suction temperature, the compressor delivery temperature, the condenser outlet temperature, the expansion valve inlet temperature, the evaporator inlet temperature, and the evaporator outlet temperature. Also record the cooling water temperatures T7 and T8 at the inlet and outlet of the condenser. Repeat the above procedures for the heater at loads of 400 watts, 600 watts, and 800 watts. After the measurements, turn the evaporator heat input to 0. Wait 1 minute and then switch off the electricity supply and then turn off the cooling water supply. You can determine the remaining required parameter values by using the equations given in the lab sheet, the pH diagram, and your measurement data. This is the end of the experiment.